Good morning. We were talking about carboxylic acids, all the different ways we can make them, and the different things that we've seen that we can do with them. One of the more unique ways that we can make a carboxylic acid, one of my favorite in theory, never done in practice ways, is that acyl addition with carbon dioxide. What a good use of carbon dioxide as a starting material. Adds one carbon to a structure, creates a carboxylic acid. And then we're talking about how carboxylic acids and their derivatives are all related. And I think that this diagram highlights why they're called the carboxylic acid derivatives. Everything can be converted back into a carboxylic acid. If it can be converted back into a carboxylic acid, if it can be hydrolyzed, then it's considered a derivative. So remind me why three of them have two different synthetic routes. Either they can be hydrolyzed to a carboxylic acid with acidic conditions or basic conditions followed by acidic conditions. But two of them just have one route listed, water. What are we distinguishing there? What's the difference between a hydrolysis that reports using water and a hydrolysis that reports either basic conditions or acidic conditions?
Water is a weak nucleophile, so those ones can be weak or strong.
Right. Because these are reported with a weak nucleophile, they can also be hydrolyzed in more reactive conditions. Like acidic conditions protonates the carbonyl. And we know that a protonated carbonyl is more electrophilic. So acidic conditions takes these less reactive carbonyls, makes them more electrophilic, more likely to react. This is a reminder that we said the acid chloride, the acid anhydride, can be hydrolyzed by water, and it has this two-step reaction, acyl addition, elimination, and then deprotonation. And remember, the addition plus elimination is substitution. So addition, elimination, deprotonation. That's what the diagram looks like if it's just water. And we add acid in, even with the reagents that can be reacted with such a weak nucleophile like water, we add acid in and it catalyzes the reaction. So it drops the activation barrier, but actually adds some number of steps. We saw the mechanism for hydrolysis of the acid chloride in water, and then we saw the mechanism for the hydrolysis of the acid chloride in acid. Which one had more steps? Hydrolysis in water or hydrolysis with acid? Right, because that catalyst is changing what happens along the way. Now there's different stages that are protonated, different stages that are deprotonated. More steps, but a lower activation barrier. That's the role of a catalyst. Okay, we are going to go through the hydrolysis of the ester as a mechanism. And I think I want to take you guys there now. So let's flip to the back side. And let's go through this mechanism that you will be tested on, the acid-catalyzed hydrolysis of the ester. Okay. Two reactions on that back sheet. One on the left, one on the right. Which one shows us the hydrolysis of an ester? The one on the right takes an ester and makes it an alcohol plus a carboxylic acid. I want you guys to make a bet before we go through this mechanism. There are 3 oxygens involved. I mean, I think arguably 4, but there's an oxygen of the carbonyl in the ester, an oxygen of the ester linkage, the OR ester, and then there's the oxygen of water. And in the product, we've got an oxygen in the carbonyl, an oxygen of the carboxylate group, and an oxygen of the alcohol. So here's the bet that I would like you guys to place. That's a weird word for it. I would like you guys to decide the oxygen of the ester linkage. That's the OR oxygen. Which oxygen is that in the product? So if I redraw this reaction that we're about to run, this oxygen in the product. That's what I'd like you guys to decide. Worksheet for you, your exam back, and worksheet in your exam back. Sorry, of course. What are your thoughts? Let me help by just labeling some of these so that it's a little bit easier for us to talk about them. Now, you have some options. We could say one option is this oxygen becomes A only, B only, C only. We could have an option where it's AB 50-50, or where it's BC 50-50. Those are the 5 options I'll give you. Maybe there's a chance 50% of the time it does one thing, 50% of the time it does another thing, right? We've seen that where competitive pathways mean different things can happen. What are your thoughts? Do you need more information? I don't have leaving group written up here, so you're going to have to elaborate a little bit more. You think this oxygen is C only? Okay. Anybody else? Do you have any instinct? If you had a 5-choice, multiple choice exam question, and right now all the information you have is what you have seen already. This is just a preview quiz. Which one are you choosing? So Justice is choosing C only. Yeah? No, you don't want me to mark it down. We could take a tally.
I chose C.
C only?
Yeah.
So that's 2 or no? Are we just on a wave now?
No, like I actually have a random.
Okay, but I mean, is everyone else just going to say C just because the first 2 said C? Really, what's your instinct? Just
I'm going with B.
B only?
Yeah.
Okay. BC 50-50. Okay, you've got 5 seconds left, and then you got to turn in the exam. What answer are you circling? Don't leave it blank, because that's a 100% chance you missed the question. I've got 4 people left that I need an answer from, right? BC, BC, C only, BC. Okay. What are you thinking there? This oxygen is connected to the carbonyl, and also it's connected to this carbon chain, so those are great places to look. Is it one of those 2 options? Now let's go through the mechanism and try to figure out how does this oxygen go through this reactive mechanism to form this. So what type of conditions are we in? Acidic conditions or basic conditions? Acidic. Is that challenging to see? It's not, right? You see the H3O+. Okay. We're in acidic conditions, so the question is, what is the base? I'm not going to consider water as my base, because if it is the base to H3O+, it just makes H3O+ in water. So what is my base? The question is the carbonyl oxygen or the ester linkage oxygen? Well, we can analyze both. And Cario will tell us which one is more appropriate. If the ester linkage oxygen acts as the base, we get this protonated ester linkage, charge positive, the acidic atom oxygen, the amount of resonance 0, well, except for the resonance that it was already able to do with the carbonyl. We saw that type of resonance all the way back in our aromatic chapter. If we protonate the carbonyl oxygen, charge, the same, positive. Atom, the same, oxygen. But resonance, different. This oxygen, when protonated, is able to engage in resonance with the ester linkage oxygen, which means the positive charge is delocalized. I worry that I confused you by saying that this could do resonance. If you show that same resonance, lone pair from oxygen, forming a double bond with the carbonyl carbon, you create a 2+ on that oxygen and a minus on the carbonyl oxygen. Not ideal. So protonating the carbonyl oxygen has 2 resonance forms, both of them equally major because full octet, same amount of charge, charge placement is on the same atom. But protonating the ester oxygen, no resonance, harder to do. It's easier to protonate something that can delocalize the charge after it's protonated. Okay, another perspective that you can take here to try and remember which of these oxygens is more likely to be the base. Because of the fact that the ester oxygen is engaged in resonance with the carbonyl, there is a partial positive on that oxygen and a partial negative on the carbonyl oxygen. Electrons flow away from the ester linkage to the carbonyl oxygen. So there's a better chance that the carbonyl oxygen is the base. It has a stronger partial negative, and it has more resonance in its conjugate base. So back to our mechanism. I'm in acidic conditions. What's my base? Either of these oxygens could be my base, but which one will be my base? The carbonyl oxygen. Okay, so protonation gives me a protonated carbonyl, and what is true about protonated carbonyls? It makes the carbonyl carbon more positive, it makes the carbonyl carbon more electrophilic. It makes the carbonyl carbon more willing to do acyl addition even with a weak nucleophile. And all we have here is a weak nucleophile. Water acts as my nucleophile. Do you recognize this as acyl addition? Because I want you to recognize it as acyl addition. If you're not sure what acyl addition is yet, put a big star in your notebook and write define acyl addition. Because it's a common step of these mechanisms, and if you don't show it, you're missing that important step of the mechanism. What's the net charge here? The net charge of my reactants in this step. Net positive. So make sure that the product in that step is also net positive. Where is the positive charge going to show up? It's showing up on the oxygen that's making a third bond. I've got this water attached. Now, I've explicitly shown the water with its 3 bonds because our next step, sorry, it's not really water. I've shown that structure with its 3 bonds because the next step is to deprotonate it. And here's the spot where I like to talk about plausibility versus feasibility, or plausibility versus pushability. I could show either of these other oxygens acting as a base to take a hydrogen away from the positively charged oxygen. That would be considered an intramolecular proton transfer. But in order to do it, 1, 2, 3, 4, this 4-membered transition state would have to form. Very tight bond angles. Very hard to actually get it to do this. What's more likely is that a molecule of water, which is our conjugate base, is more likely to run into this molecule and deprotonate it, and then in another step, protonate the way that we expect. So when I ask you to show me this mechanism, I don't want you to invent steps, and I don't want you to compress steps or combine them. It is most likely that water here acts as a base to run this deprotonation first. And then acts as a proton donor. There are mechanisms that textbooks will produce, and the mechanisms will skip over this step. They won't show any arrows. They'll skip over this step and just say proton transfer. A hydrogen will leave this oxygen, and a hydrogen will move to the next oxygen. And they won't demonstrate arrows as if it's too challenging to show. It's not challenging. A little tedious? Sure. Well, I've reformed my acid, so I should be considering what to protonate next. If I have 3 oxygens up there that could be the base. I have an OH, and the ester linkage, the OR. 3 oxygens that could be a base in this step. If I protonate either of these alcohols, I just reverse the step I just did. So how many of the oxygens should really is really able to serve as my base? Just 1. If I want to show the mechanism doing something different, there's only one choice. If I want to reverse the mechanism, if I want to take what I'm getting closer to my product and send it backwards, then I have two choices. But if I want to do something unique with this mechanism, I only have one choice. This reaction, hydrolysis, is a type of acyl substitution. True or false? Hydrolysis, like this, is a type of acyl substitution. True or false? Hydrolysis, like this, is a type of acyl substitution. Raise your hand for true. Raise your hand for false. It's not a type of acyl substitution. Raise your hand if you didn't raise your hand yet. It is. It is a type of substitution. I'm substituting this entire group for just an OH. So somewhere, somehow, we're not quite convinced yet about what the role of this oxygen is, but we are convinced that it's substitution. Do you remember how we get to substitution if we're not just doing simple SN1, SN2 substitution? Substitution is addition followed by elimination. Or actually, you can do it by elimination followed by addition. Which of those two steps have I done already? Addition. So which of them still remains? Elimination. I need to show an elimination step. What's my leaving group? Justice, I think you have this one. Right. That positively charged oxygen is a good leaving group. From which carbon? Should the positively charged oxygen break off from the carbon chain on the right and leave behind just a regular carbocation? Or should this positively charged oxygen break off from the left where there are two available oxygens that can share a lone pair and stabilize the positive charge, leaving you without a carbocation? Should the leaving group form a carbocation or avoid a carbocation? Yeah, if there's a way to avoid a carbocation, let's show it, which should remind you of the acetal mechanisms. We're doing the same thing, protonating one of the groups and then doing elimination. One of those two groups shares its lone pair. Which one needs to share it? Doesn't matter. You wouldn't be able to prove which one. Well, actually, you could. It doesn't matter because both of them share it. It could be either one. It's a 50-50 chance. Is that it? Is that my final structure? Close, but not really. Remember, this is acid catalyzed hydrolysis, and I have not reformed my acid yet. My acid is still consumed in that protonated carbonyl. So my last step, deprotonation to reform the acid. Do you guys recognize this reaction at all? Those of you taking lab this semester? This is the hydrolysis of banana oil. Banana oil took isopentyl alcohol and acetic acid and made isopentyl acetate, or banana oil. Okay, what was the final conclusion? Back to our original multiple choice question. Correct answer was C only. Now, if we were tracking the carbonyl oxygen got protonated, and then the carbonyl oxygen got mixed up within the two alcohols. There's no way to know which of these oxygens was the carbonyl oxygen originally. So in our final product, the carbonyl oxygen might be A, might be B. No way to know. The carbonyl oxygen is some 50-50 mixture of A and B. So this answer, A, B, 50-50, that's a real explanation for what one of the oxygens did. But this ester linkage oxygen never left this carbon chain. This oxygen carries this carbon chain with it the entire way. This oxygen leaves as the alcohol. Questions on that mechanism? Okay. The process of hydrolyzing an ester in basic conditions rather than acidic conditions is referred to as saponification. I want to demonstrate how being in acidic conditions is so different from being in basic conditions. Let's just look at a quick mechanism for saponification. By the way, saponification, I think it comes from the Latin for soap making. This is the process by which soap is made. This is a process as old as mankind. Humans would harvest animal fat and then mix it with water and ash from their fire. The ash actually contained hydroxides like potassium hydroxide. Actually, potassium itself gets its name from pot ash. The ashes that you rake up after you've had a fire get harvested, and you can collect potassium from it, giving us potassium. So potassium hydroxide in the char, in the coals, mixed with animal fat and ester, saponifies and gives us our carboxylate. So let's take a simple structure like ethyl acetate, and let's show what that saponification looks like. If we want to show it getting to a carboxylic acid, saponification has to finish with an acid workup. If you're going for soap, you don't do an acid workup. You want that carboxylate. If you're going for a carboxylic acid, we go for an acid workup. Where did this oxygen come from in the starting material? Is this the oxygen of the carbonyl, the oxygen of the ester, or the oxygen of hydroxide? The ester. We just proved that with the last mechanism, that this carbon chain stays with this oxygen. So let's make sure that that happens again here. Basic conditions or acidic? Basic conditions. So should I start by trying to protonate something? No way. There's no proton donor available. So what should my base do then? I want my base to act as a nucleophile. I need to get that OR group to leave. To get it to leave, I need to turn this into a tetrahedral intermediate. In acidic conditions, what charge did my intermediates have on them? Doesn't that make sense? My acid is a source of H+, so my intermediates should be positively charged. Do you see a positive charge in this intermediate? Doesn't that make sense? We're in the absence of H+. Why would there be any positive charge? Acidic conditions and basic conditions couldn't be more different. They're quite literally the opposites of each other. I guess maybe the only thing they have in common is acyl addition followed by this elimination step, which is what gives us substitution in the first place. Notice that I drew out the OH bond of that new carboxylic acid. Carboxylic acid, much stronger acid than an alcohol. An alkoxide, a much stronger base than a carboxylate. This has some very significant acid-base equilibrium. This is a strong base, and this is a weak acid. So they will react by acid-base chemistry. Oops. That's how we get our alcohol via hydrolysis or saponification. And if you were using this to make soap, you've used potassium hydroxide, perhaps, and you've just made a potassium carboxylate. Especially if you're using animal fat, this carbon chain is 17 carbons long or more, and you've made a good amphiphilic soap, something that'll grab onto your dirt and grease and dissolve into water. If you're not going for saponification and you're actually going for base catalyzed hydrolysis, then our last step here is adding that acid workup to show the protonation of our carboxylic acid. Either way, acid catalyzed or base catalyzed, we can always predict which oxygen goes through what role at what step. We can always predict where the ester oxygen ends up and where it came from. Okay, questions on this mechanism? All right. Now for a challenge. I would like you guys, you're all caught up on what's on the board, or do you need a picture? Okay, I'll leave what's on the far right. I'll just clear this space. I would like you guys to work in groups, and I would like for you to predict a mechanism for the acid catalyzed hydrolysis of acetonitrile into a carboxylic acid, into acetic acid. This also gives a byproduct of ammonia. This is a challenge because now you have to try and decide, again, when should proton transfers happen and how, but what plays what role at what time? Can we get into groups of 3 or 4 and discuss what you think is going to happen? How similar do you think it will look to the esterification mechanism? Use that as a template. How different might it look? How can you use difference in electronegativities to make predictions? I'd like to come around and see how things are going. Not a mechanism you're tested on either, by the way, which means this is one that I want you to really just discuss through. Because if you can make predictions about this mechanism, it will help reaffirm things that you need to know about the esterification mechanism. How did your esterification mechanism start? You're in acidic conditions, so protonation makes sense as a first step, doesn't it? You didn't really take this group's working, but the rest of you didn't really take the hint to work as a group. I want you to discuss it. It's good if you've got ideas. Share those ideas. I actually don't care if you carry the team today. That's fine. Carry them. Bring them with you. If you've got ideas, good. If you don't have ideas, grab somebody that does. I think that means, yeah, you might have to move.
We know that the nitrogen is protonated.
Yeah, then maybe I can have you just scoot forward and listen to these two talk.
So the anions becomes protonated. The lone pair. Because the OH can't. What would that? Because you need to get two oxygens. I'm always smiling. But that's not really that's not a good way to show protonation. That is.
Oh, yeah.
But honestly, if you want to shortcut this one, that's okay. I think even if you can predict what the intermediates are, that's a good process. It wouldn't make sense to protonate that oxygen, would it? Because that would just reverse the mechanism. So there's really only one other thing to protonate. Yep. Okay. Good work, guys. I'm going to catch up to where a lot of you have already gotten. I'm just catching up to where you are. You have to protonate what? Oh, okay. At some point, probably.
Can I assume
You didn't. Yeah, you did. You're right here.
Okay.
Yep. Sorry. No, I guess actually you did. You did.
Can I assume, because now I've used NH2, or not, well, the H2O and H2O plus, can I assume we have more water?
Yes, you can. Actually, that's a good assumption. You should use 2 equivalences of water because you have no oxygens in your nitrile and you need 2 oxygens in your carboxylic acid. So there will be 2 equivalences of water that actually play a role in the reaction. So I like to show them at each step. You can do that too if you want to. Hey, I want to pause you guys. A lot of you got here. Do you know what this is? Oh, it is kind of an imine. A little bit. It's a CN double bond. It's a protonated imine, but it's a little bit unique in that it has this oxygen. Would you believe me if I said this is a resonance form? A resonance form of what? What would change from this resonance form to another? Electrons would flow from oxygen or to oxygen. Well, if I flow electrons to oxygen, there's no pi bond to flow to, so I'd have to just break the sigma bond. But that's not resonance then. Toward nitrogen, yeah. If my oxygen shared electrons and let nitrogen take the electrons back, I am going to flip it. I'm going to flip it a little bit, but when I form that double bond, what's that? What is that? Oh my God, what is that? That's a protonated amide, isn't it? Take an amide, carbonyl to N, and protonate the oxygen. This is what you get. So far, what you guys have done in your mechanism, you've all successfully predicted how to take a nitrile to an amide, but actually just a protonated amide. What I'm demonstrating for you right now is that if I had asked you to show the hydrolysis of an amide, you would start right here. The hydrolysis of a nitrile includes the hydrolysis of an amide, but requires more steps to get there. And doesn't that make sense? The nitrile and the amide are similar to each other. So to hydrolyze the amide is part of the hydrolysis of the nitrile. Okay, now that you've got that perspective, that you have taken your nitrile and essentially brought it to being a protonated amide, it should now look a lot more similar again to the hydrolysis of the ester. Instead of protonating the ester carbonyl, you've just protonated the amide carbonyl. What did you do after you protonated the ester carbonyl? What should you do now that you're protonating the amide carbonyl? Do you see that perspective? I've asked you to master the esterification mechanism, because if you can master the esterification mechanism or the hydrolysis of the ester mechanism, you can master any of them. You applied pretty much the exact same rules to start the hydrolysis of the nitrile, and now you're going to apply the exact same rules again in what looks like the hydrolysis of an amide, which is really the wrapping up the hydrolysis of the nitrile. A lot of blank stares for doing such a good job.
Is this right, or do we have to use that resonance form?
You do not have to use that resonance form. I only pointed out that resonance form because I don't think you would have seen the structure on the right and thought, that's a protonated amide. But it is a protonated amide. And both are well, actually the resonance form on the right is a more major resonance form. Better charge placement. What you guys have shown is perfect. Yep, you're on the right track.
Did I do it right?
Oh, I wouldn't predict this though. I wouldn't predict making a negative charge on one oxygen while keeping a positive charge on the nitrogen. If you look back at our esterification mechanism, you're very similar to this step, where you've got two OHs and a protonated leaving group. And the next thing that we did was not deprotonation. Two OHs and a protonated leaving group. But you are not going to do deprotonation yet.
Did I do it right?
Yeah, great. Awesome. Where are you at? No, so far it's... Yeah, you got to this. That's the protonated amide. Acyl addition, deprotonation, protonation, elimination, deprotonation. Nailed it. Exactly right. Great work. You got the same thing? Okay. Oh, you do have something different. That is substitution. But substitution here won't happen. What does happen? Okay, actually, this is resonance. Do you agree that's what I did up there in orange?
Oh, yeah.
And resonance has to be related by a resonance arrow. And it's okay to show those resonance forms, but this protonated amide behaves a lot like our protonated ester, where it goes through acyl addition. So this protonated amide should also go through acyl addition rather than going through protonation. You're actually, in this step, you're proposing two things. You're saying it must, I don't know if you know that, but when you write a mechanism, you're saying it must. It must protonate the nitrogen and deprotonate the oxygen at the same time. That's actually quite hard to do. You need 3 molecules to all line up at the exact right orientation with the right amount of energy at the exact same time in order for all of that to happen at once. It's much more likely that less is going to happen at any given time. And what we should expect is acyl addition. That carbonyl gets attacked by water. So take a look at Pamela's. She's got a good solution there. You don't have to show that resonance form that I showed up there, but if it helps you
make your next prediction, then it's great. Oh, I got lost here.
Sorry. It's like a little zigzag.
It is, but that's the way it should be. Yep, nailed it. How are you guys doing? Yep. Great. How are you doing? Okay. I'm going to keep going up here. We've got that first equivalence of water that added. Now we've got this protonated carbonyl. And just like last time, our protonated carbonyl goes through acyl addition. You could show this on either resonance form, though. So if you're not drawing this second resonance form, you can show acyl addition over here. It just doesn't look like acyl addition because it doesn't look like a carbonyl group. Instead, you're breaking the CN bond. I'm going to keep with what my arrows already show, and I'm going to attack over here, open this. Do you remember in the esterification or hydrolysis of the ester mechanism, we got to this exact type of intermediate. We had the oxygen, we had the ester group, but now it's just an amide group. Oops. I've got my water to act as my conjugate base, which means after acyl addition, I should expect to do deprotonation and then protonation. Why should I expect to see that? Because that's exactly what we saw before. We saw deprotonation and then protonation. What should I protonate? If I protonate either of those OH groups, I just reverse my last step. So just like in the hydrolysis of the ester mechanism, I want to protonate what my leaving group is going to be. I want to get rid of this nitrogen. So I protonate my leaving group. Now that I've got a good leaving group, because it's positively charged, one of my oxygens reforms the carbonyl, just like we saw with the hydrolysis of the ester. At this point, I've got my protonated carbonyl, I've got my ammonia, and I've got water. I will admit, in terms of plausibility, it is a lot more likely here that ammonia acts as the base over water. Why is ammonia a better base than water? Well, they have the same charge, but the base is either an oxygen or a nitrogen, and nitrogen is less electronegative, more willing to share electrons, better base. So just because I showed this as the product we were going for, I'm going to just leave that as our final product there. But that idea that it could have been either one acting as the base holds true. Okay, keep in mind that you have just learned hydrolysis of the ester, and that's a mechanism I'm going to ask you to show a number of times. You have homework on it, and you have a unit test this weekend where it might be on it, and you have the final exam coming up where it might be on it. But you took the skills you learned from hydrolysis of the ester and you hydrolyzed an amide by way of hydrolyzing a nitrile. So although you only learned hydrolysis of the ester, you now can apply the exact same skills to hydrolysis of the nitrile and hydrolysis of the amide. Nothing different about them. So when I ask you to show the hydrolysis of the ester, it's not because it's the easiest one or it's the best one, and it's not because the others are harder. It's just because if I focus your learning on that mechanism, you can master it and apply all of the same skills to anything else. All right. Some more of the reactions. I want to go through a few of these. We're going to come back later. We're going to do the acid-catalyzed esterification mechanism as well. But I want to make sure that we've covered some of these other reactions. So we've talked about hydrolysis of the ester on this little diagram. The hydrolysis of the ester, hydrolysis to the carboxylic acids, acidic conditions, basic conditions, sometimes neutral conditions. Now let's turn our attention to the other direction. From the carboxylic acid into each of the derivatives. So we're talking about the acyl derivatization of the carboxylic acid. We have already talked about the carboxylic acid becoming an acid halide using thionyl chloride. And is this where I made the mistake? No, this time actually it showed it correctly. When was the first time that we used this? We used it in the aromatic reactions. We said if we have a carboxylic acid, we can turn it into an acid halide, and we can use that for acylation. The process of taking a carboxylic acid and bringing it to an acid anhydride, this is a dehydration reaction. We're going to use P2O5, and here's what I want you to know about P2O5. We call this a dehydrating reagent. It chemically extracts water out of two carboxylic acids, takes two carboxylic acids and combines them as an anhydride. And I do want to point out that this reaction works best for symmetric anhydrides. Why? Well, let's give an example. If I have a mixture of benzoic acid and acetic acid, and I mix them together in the presence of my dehydrating reagent. Even if my mixture is 1-to-1 benzoic acid and acetic acid, there is too often a possibility of two benzoic acids reacting and two acetic acids reacting, as much as there is the possibility of forming the asymmetric anhydride. So this process gives me three different structures as possible products. I might get the asymmetric acetic benzoic anhydride. I might get the symmetric benzoic anhydride. I might get the symmetric acetic anhydride. So if I'm trying to make an asymmetric anhydride, this isn't the way to do it. If I'm looking to make a symmetric anhydride, this is a great way to do it. Forming the ester. Perhaps the most famous method of forming the ester is Fischer esterification. Those of you that are in lab have done this a number of times. No, not a number of times. You did it once with banana oil, and you're going to do it again the next 2 weeks with your lab project. You're going to be using more Fischer esterification. A better name for that is acid catalyzed esterification. It is the exact opposite of the reaction we just did earlier. We're going to come back and do this mechanism as well. And that's the carboxylic acid to ester using alcohol and an acid. When we take a carboxylic acid to make an amide, we need some amine and this reagent DCC. This is, once again, a dehydrating reagent. And it, once again, chemically extracts an equivalence of water to help in the production of the amide. Let me ask you this. What reagent do you think DCC is most likely to be mistaken with? PCC. So how do you differentiate between PCC and DCC? If you know their names, that might be useful. Pyridinium chlorochromate. When you hear chromate, you should think oxidizing agent. DCC, dicyclohexyl. I always forget actually what the second C is for. It's like carbandiamide or something. It's this NCN structure. You can see the equivalence of water that gets taken out. Each nitrogen takes a hydrogen, and the carbon in the middle becomes a carbonyl, takes on the oxygen. Dehydrating, DCC. Oxidizer, PCC.
We don't have the H and R2.
What did I put?
Nothing. We need to have that.
Oh, yeah. Okay, thank you. Yeah, if you'd add that, please. In the same way that you cannot make an ester without an alcohol, you cannot make an amide without an amine. So you should have that amine written over the arrow as well. DCC and amine. Thank you. Okay. Those are all the ways that we can derivatize the carboxylic acid. A few other acyl derivatizations. I want you to notice how the remaining derivatizations on this diagram only move from more reactive carbonyl to less reactive carbonyl. And that should make sense. A more reactive carbonyl can be reacted with to become something more stable. But something that is more stable is challenging to undo and make something less stable. The exception there, of course, is that everything can move towards and from a carboxylic acid. So the carboxylic acid can become a more stable carbonyl or a less stable carbonyl. But the acid halide can form all of our other derivatives. But none of the other derivatives can form the acid halide. So I'm gonna just simply model this as taking a more reactive derivative to a less reactive. I want you to notice that whether you're forming an ester from an anhydride or from an acid halide, you use the same reagents. So if we want to go towards an anhydride, we have to go from something more reactive. What's more reactive than the anhydride? The acid halide. So our only starting material possible here is towards the acid halide. So we take an acid halide, react it with a carboxylate. This is a good method for making an asymmetric anhydride. Start with the acid halide of whatever group you want on one side, and provide the carboxylate of whatever group you want on the other side. Where P2O5 was not a good reagent for making asymmetric anhydrides, this is a good reagent for asymmetric anhydrides. How many steps do you expect this mechanism requires? One step, 2 steps, 3 steps, or 4 or more? Is it a 1-step mechanism, a 2-step mechanism, 3-step, or does it take 4 or more steps? 1 step? 1 step? By 1 step, you mean like all the bonds made and braid happen at made and broken happen at once. 1 step. 2 step. I've got 2 for 1 step, 1 for 2 step. What do you see in your head? What bonds made and what bonds broken do you see at each step? What are you expecting to happen in 1 step?
What's
Carboxylate.
Oxygen will attack the carbonyl of the acid halide while it kicks off.
What is the weakest bond? What bond is most easily broken? The pi bond is most easily broken. So if something attacks the carbonyl, it cannot do SN2. Actually, SN2 on a trigonal planar carbon is impossible. Won't be done. And part of that is because that's not the easiest bond to break. There's a much, much easier bond to break, which is the pi bond. So first, the pi bond breaks. But that does not give you 1 step. Then the pi bond reforms and kicks off a leaving group, elimination. Addition, then elimination is substitution. So this is not a 1-step substitution. This is an acyl substitution. Let's demonstrate what that looks like. Again, I'll take this example of trying to make an asymmetric benzoic acetic anhydride. What I'm going to decide to do is take benzoyl chloride and react it with acetate. I could have gone any direction there. I could have taken benzoate and reacted it with acetyl chloride. I've got 1 carboxylate, I've got 1 acid halide. We see acyl addition. Look how close that is to already being an anhydride. It's got 1 carbonyl bonded with the oxygen to the other carbonyl carbon. It's just that I don't have another carbonyl carbon yet. So I do elimination, kick off my chloride, and I've formed my anhydride. Whether symmetric or asymmetric, this is a great method for making an anhydride. I'm not showing the chloride that got kicked off. But remember, the acid anhydride is less reactive, so this process does not reverse. Favors the forward direction. If we want to go towards an ester, we can take either an acid chloride or an acid anhydride. react it with an alcohol. The problem here is that the conjugate base, chloride, that gets kicked off from the acid halide, or carboxylate that gets kicked off from the anhydride, these conjugate bases are not strong enough to deprotonate that oxygen from the alcohol. This will be the last step that happens in their mechanism, but they require a deprotonation. They require a stronger base. So we add pyridine. Do you guys remember the structure of pyridine? Pyridine is an organic base. And we need an organic base because we can't use, well, there's nothing here for me. We can't use hydroxide. We know that hydroxide will hydrolyze our carbonyls. So pyridine acts as an organic base, which is good for our deprotonation step and doesn't impact the formation of our ester. Pyridine, is this six-membered ring that looks like benzene, but has a nitrogen inside of it. Because pyridine acts as the base, what we're left with is pyridinium. We're either left with pyridinium chloride or pyridinium carboxylate, but pyridine is acting as the conjugate base there. So let me demonstrate not the entire mechanism, but just the role that it plays. This is basic conditions, not acidic conditions. So at the very last step, after my alcohol has attacked and either kicked off chloride or kicked off a carboxylate, I have to deprotonate the oxygen. It's a slightly different mechanism than what we saw before. Our last step before was deprotonating the carbonyl. Here I need to deprotonate this oxygen. The problem is that these conjugate bases are just not strong enough. So we use pyridine instead to solve that problem. Okay, and lastly, toward an amide. It is possible to take an ester and turn it into an amide. It is just not commonly done. The ester is more reactive than the amide, so the ester can be upscaled, upcycled into the amide, but it's just not common. So we're not going to show it. Instead, we're going to assume the same thing here. We're going to say the acid halide and the acid anhydride can be converted into an amide. What do you notice is different about the reaction to make an amide compared to the reaction to make an ester? Making an ester required pyridine. Making an amide does not require pyridine. What it does require is excess amount of the amine. You guys did this in lab last week. Those of you that had me in lab, you heard me say the amine plays two roles. The amine plays the nucleophilic role to substitute the chloride or to substitute the anhydride. The amine also plays the role of the base. Where pyridine came in to deprotonate the ester, we simply use a second equivalence of the amine to deprotonate that intermediate. Once again, chloride, not a good base. Carboxylate, not a good base. But if I have excess of this amine, that is just as good of a base as pyridine. And so we can rely on the amine to run that deprotonation. The only other derivation that you guys see on here is toward a nitrile. This is the one time that we can't start from an acid halide to go to the less reactive derivative. The acid halide, of course, has no nitrogen in it. But if we start from an amide, we can remove an equivalence of water. This is not clearly written on there, but it has to be an NH2 amide. It can't be an amide that has carbon chains. Last week you guys made DEET, diethyl amide, where your nitrogen had 2 carbon chains coming off. Wouldn't have been effective at making a nitrile. What is this reagent again? P2O5? What role does it play? Dehydrating, meaning it needs an equivalence of water. Where will it get that equivalence of water? From the H2 and the O. If it's not an NH2 amide, doesn't go through dehydration. Questions about the carboxylic acid and derivatives reactions? Okay, just a few more items. First, the reactions with organometallics. Once again, only looking at organolithiums and Grignards, because these are the good nucleophiles. The cuprate will actually come back. What we see is that the acid halide, the acid anhydride, the ester all react with Grignards to add 2 equivalences of the Grignard. Remember that the aldehyde and the ketone only gave 1 equivalence. So for example, if I had the aldehyde and I reacted this with my phenyl Grignard and then an aqueous workup, I would only expect 1 equivalence to add. So why does the acid halide, why does the ester, why does the acid anhydride give 2 equivalences? Let's compare it. We know that this mechanism proceeds by the nucleophilic carbon attacking and opening the carbonyl. And then we know that that aqueous workup plays a role in protonating the alkoxide, giving us an alcohol, and destroying what's left of that Grignard. So what happens differently when we have an acid halide? Well, things that we already know. The acid halide gets attacked by a nucleophile in ways that we've seen to give this tetrahedral intermediate. And just like we've seen, this tetrahedral intermediate collapses, it reforms a carbonyl, kicks off the chlorine. What functional group have we made? I know you know this. What functional group have we made at this point in the mechanism? A ketone, which were some of the first functional groups that we reacted with organometallics. Ketones are reactive to organometallics. The aldehyde got opened into an alkoxide. The acid halide gets substituted into a ketone, and ketones react in the presence of organometallics. So all of these derivatives that have some good leaving group, they react with organometallics in two equivalences. They add two equivalences of that Grignard, and they become a tertiary alcohol. What two functional groups don't react like this? The nitrile and the amide. So let's talk about why. If I attack an amide, I'm going to put that as NR2. With my Grignard, I don't have a good leaving group. The carbon-nitrogen bond is too strong. The carbon-nitrogen bond won't break off. The carbon-chlorine bond left because it was a weak bond. But here the carbon-nitrogen bond won't react. So this is as far as it goes. It stops here. And then we introduce acidic conditions. This is a hemiamine. You remember the hemiacetal was halfway between an acetal and a carbonyl. This is halfway between an imine and a carbonyl, which means that this is hydrolysis of an imine. That's what we're looking at. Now that we've added acidic conditions, this hemiamine gets hydrolyzed. And what we learned last week with aldehydes and ketones is that the hydrolysis of the hemiamine, or the hydrolysis of the imine, forms a carbonyl. The presence of the nitrogen changes everything. Same thing would be seen in the acyl addition of the nitrile. When the organometallic opens the nitrile group, it leaves us with what looks a lot more similar to the imine. This is a deprotonated imine. And this is as far as it will react. The CN double bond won't be attacked again because that's going to force a 2- onto the nitrogen. The nitrogen just won't be stable with that. So the nitrile only gets one addition. The amide only gets one addition, but all of our other functional groups able to attack with 2 additions. Hydrolysis of the imine back to a ketone. I wanted to review a few of the reactions with esters. This is what you see on the bottom right. The reaction that comes in from the right, a ketone to an ester. Do you remember the name of this reaction? I wouldn't either. A ketone becoming an ester using a reagent we're familiar with, peroxy acid. This is the Bayer-Villiger oxidation. So I'm using this opportunity to remind you about this unique oxidation pathway for a ketone. Ketones can't always be oxidized, but they can be oxidized into an ester. From an ester, I want you to see how we go from having phenyl acetate, that's our ester in the middle of the diagram, and the reaction that goes up takes an ester and makes it a different ester. This is what we call trans-esterification. Start with an ester, make a different ester. This reaction is also heavily impacted by equilibrium. You've got two different alcohols at some point trying to react, so there's a lot of work to do. What's that reaction that goes straight down? This was a name I put up on the board earlier today. Start with an ester, react it with hydroxide, be left with a carboxylate. What is that? Start with an ester, make soap. Saponification. Okay, lastly, we have already reviewed the reduction of most of our derivatives. We found that we could make primary alcohols back in our alcohol chapter. We found that we could make primary alcohols by reducing these primary carbonyls. Primary alcohols from acid halides, acid anhydrides. Oh, I don't even know how to draw that. That's a weird one. Acid halides, anhydrides, esters, acids. But as it turns out, that CN bond is very hard to break. So when we reduce a nitrile or an amide, we get an amine. We don't get an alcohol. The nitrile is always going to produce a primary amine. The nitrile has no other carbon groups connected to the nitrogen. So the nitrogen always becomes NH2. The amide, on the other hand, the amide breaks none of the carbon-nitrogen bonds. So however many groups are coming off of that nitrogen, that same number of groups stays present. It's quite different from the others. All of the other ones get rid of whatever side chains they have and reduce down to a primary alcohol. The amide doesn't get rid of any of the carbon chain. It just reduces the carbonyl down directly to an amine. We have not covered a lot of different ways to make amines. We've hardly worked much with amines. We worked with amines a little bit last week, aldehydes and ketones, making imines and enamines. We've worked with amines here if we want to make an amide from a carboxylic acid or an amide from an acid halide. But we've not shown a lot of reactions that make amines. This is a great reaction to make an amine with. create an amide that you want, reduce the amide. Now you have an amine that has all of that same bonding character. Amines are challenging. In fact, there's an entire chapter on amines that we're going to not do this semester. Amines are challenging reagents to work with because they are both strong bases and good nucleophiles. So trying to do substitution with an amine just once is hard to do. It can do substitution, and then it can do it again, and then it can do it again. And sometimes amines keep substituting until they become quaternary ammonium ions. So we don't show a lot of synthesis of amines. This is one of the few times that you'll see it. Tomorrow, we're going to do the acid-catalyzed Fischer esterification mechanism. So that's forming the ester. Not a challenging mechanism based on what we've already gone through today. So we're going to go through that mechanism tomorrow. But I also want to spend 10 minutes tomorrow having you design a synthetic pathway where you start with one functional group and take it through at least 3 steps to a different functional group, and then trade off with each other to try and solve each other's syntheses. The challenge is to get you to think about what pathways work, what pathways don't, and just make a path. Okay. You got a question? Oh. So tomorrow's our last day before the unit test as well. So feel free to bring the homework in so that you can work on the homework while you're in class tomorrow. Have a good day. Thank you guys for your time. I'll see you tomorrow.